So how am I going to deform those three contours? I'm going to do the following. So this is a contour C2. Eventually, the only integral that will be left is the integral with respect to C2. And so what I have to do, let me choose a point Z on this contour C2. I'm going to call this point C1. Then what do I have? I have an integral which is a contour around C1, and the C1 is slightly outside. So the way, and it runs in the same direction as C2. So what I'm going to do, I'm just going to deform that contour. So it just circles around my particular point Z2. Okay. So again, I'm doing this, keeping fixed the point Z2. I will integrate over all possible Z2s later. And I'm going to bring the contour C1 that it runs along the C2 everywhere except this special point. Okay? So this is my contour C1. So what do I have there? I have still left an integral with respect to dz1 over 2 pi I, right? So I have J1 of Z1, right? Because on this contour C1, I'm integrating charge Q1. So that's the integral of J1 Z1. So this is an integral with respect to a contour C1. And then I have a charge, I have a current located at Z2. So I'm just going to write it down, J2 of Z2. Right? So notice that I do not have somewhere up here, I would have to remember that I have to integrate with respect to Z2 over 2 wherever I have left. Okay? So that's the first piece. So the second piece, I have the contour with the minus sign, and that's a contour with respect to the C3. So I have C3, right? Then I have dz3. So dz3 over 2 pi I. And then here I have J1 of Z3. And then here I have J2 of Z2. I still have left the integral with respect to Z2 variable. So now, normally my contour C3 must be inside C2, and it must be a nice round contour. But I'm just going to deform it, okay? And so the contour C3, I'm just going to deform it that it actually follows the contour C2, and it just, in order for it to be inside, I must move somewhat inside around this point Z2. So I make this small semicircle. Now the minus sign up here, I can flip into a plus sign. Okay, so I can put the plus sign, and I'm going to change the orientation of the C3 contour, right? Okay. So notice that in this picture, what is happening, I am computing the integral around C1 and the integral around C3, right? So this is C3. And so what I could do, except that at this point, I can squeeze those two contours on top of one another. One contour runs in one direction, and one contour runs in other direction. And so this integral is going to end up being so the integrals away from the point Z2 will cancel, right? And the only thing I will be left with, so let me draw the picture first. So I will be left. Again, so I have the contour C2, and so this is my point Z2. So the only not cancel p's in the integral because everything else will be the same. Will be this small integral around point z2. And so this will make up a full contour, and it will actually be C1 minus C3. So in other words, keeping in mind, well, okay, I can actually write down everything completely. So let me keep my notations. So, so the commutator between Q1 and Q2 on a contour C2, right? So it's going to be equal to, I have an integral with respect to Z2 variable, 2 pi I. So that's the outside integral. And inside, so I have an integral C1 minus C3, which is the integral around that small circle, and I can make it as small as I want, right? By doing the deformation. And so here I have d, I'm going to call it dz1 over 2 pi I, and then here I have j1 of z1, j2 of z2. Okay, so is there any questions at this stage? Yes?
From the equation, it seems to be already changed the order of J1 and J2 in a second.
Why? Oh, it doesn't matter. Those are just functions, right? I mean, you might worry about the order if there is a if they are fermionic, right? But those guys are just fields.
Okay, but we are going to define the operators.
The operators are defined once they take, so this line up here, those are just functions, right? Which classical functions. In order for me to get operators, I need to stick those functions inside the constraint. After I take this difference between functions, write down a path integral outside, then I will get the operator. But actually, all the operations that I am doing right now are the operators with other kind of things with the functions itself. Right? So up here, when I write down the operators, what I mean is that this combination is inside the path integral. Right? But still, inside the path integral, I just have a normal functions. So it's only when I start computing, so it's the next step that I'm going to do, that I now make a sort of, in this next, so here we actually evaluate path integral. Right? So I haven't done any computation of the path integral so far. Everything is the functions, order doesn't matter. Which is, I agree with you, it's misleading because here I'm writing down operators, meaning that I already evaluated the path integral, but it's not. Where I evaluate the path integral is at this side. Okay? So what do I have? So I will have still the integral C2 dz2 over 2 pi I. And so now when I plug this in the path integral, then here I have two fields inside the path integral. And so I'm asking the question, what the OP is here, right? And the OP is, what I would need to do, I need to find the residue of these guys as Z1 approaches to Z2. And so this integral will pick up precisely the residue. So here, when I write it down in this way, Z1 goes to Z2 residue. Actually, even here, I don't need to evaluate the path integral. Okay. So I'm going to, because in this case, I'm going to write it down as a residue. So those are two holomorphic functions. And so the integral here is just the residue of this product. So I have residue Z1 goes to Z2, G1 of Z1, G2 of Z2. Right, so normally there will be a singularity in this product after I evaluate the path integral. And so that's why I will get a non-vanishing residue. Okay, so very good. I don't know. I'm not. I'm saying that evaluating the path integral will simply force me to rewrite exactly the same thing. There will be no more changes. Because the only thing I have to do now is, you know, that the question is how do I evaluate the residues? And that's where I use the knowledge that inside, that once those guys are inside the path integrals, there are quantum corrections. And the quantum corrections are accounted for by cross contractions. And so I have to do the appropriate cross contractions and pick up the residues that one process. So actually, what I said first was correct. That this line is we evaluate path integral. Because now, once I know that there are singularities, I know that this integral just becomes a residue, right? So the singularities will come from the OPEs. So in other words, I need to have in mind the OPE structure. Right? Yeah. All right. So any questions? Okay. So now you can see why I needed 3 contours, because as I promised you, I end up having to do only single integral. And the other 3 integrals ended up being just a computation of a residue. Okay, very good. So what I did so far was in case of a conserved, 2 conserved charges, but it doesn't have to be so, right? So we can construct, we can take any operator and repeat this game with an arbitrary operator. In fact, it doesn't have to be a holomorphic operator. And so in this way, I can construct a commutator between a conserved charge Q and an operator. So Z2 bar. As I'm saying, it doesn't have to be holomorphic. So this is around some contour C2. Actually, when I write down this, I keep so Z2 is a coordinate on the C2 contour. So this will be equal to a residue. Z1 goes to Z2, a current J of Z1, A of Z2, Z2 bar. So this line here, this is just a generalization, what I have up here. So the only thing is that I dropped the contour integral with respect to Z2. And so this Q1 becomes just instead of a charge, I will have a current. And in the residue, I have the OPE. So here I have the OPE of 2 currents. And so this A, it's defined on a contour, and so it plays the role. It plays the role of the current into Z. However, we already know with you when we asked the question, how does our how does our field transform with respect to transformations generated by some currents? And so what is written here is precisely 1 over I epsilon delta A of Z2 bar. So this we established before. So we studied in what identities? And so right now what we established the left-hand side of this identity, which is even more familiar. In order to get a variation of any operator with respect to some symmetry, all we have to do is to add to compute a commutator of corresponding conserved charge with a given operator. That will tell us what the variation of the operator is. Okay, good. So, so the moral of the story, OPEs will produce for us commutator algebra And since we are already very familiar with OPs, we can go ahead and look at various algebra. So our first example will be Virasoro algebra, which is an algebra of conserved Virasoro generators. Right? So those are infinite set of conserved charges associated with the stress energy tensor. Right? So I can construct a JM. So this is holomorphic Zm plus 1 T of Z. So this is a holomorphic current. So it's a conserved current. Using current. So current. So I can now construct a charge corresponding to this conserved current. So conserved charge Qm is going to be equal an integral of dz over 2 pi I of Jm, much like we did in general. And so in this case, you can see that I can write it down as dz over 2 pi I z, z to the m plus 2 T of z. Okay? And that's exactly how we define our Virasoro generators. So Virasoro generators are conserved charges. Are conserved charges corresponding to this conserved charge. So those are our Virasoro generators. And so now we can construct a Virasoro algebra by asking the question: what is a commutator? What is a commutator between two charges, right? So here I have a commutator Lm, Ln, and so according to our general formula, so this commutator must be equal to a contour integral. So this is around the contour C2. So here I have dz2 over 2 pi I, and then I have a residue as z1 goes to z2. I have Jm of z1, Jm of z2. Okay, so what I'm doing here, I'm simply using this general expression we derived. The commutator of two charges is the integral over contour z2, the residue of the currents, right? So our charges, so once our current is J mu, the corresponding charges are just Virasoro generators, and so that thing will compute precisely the Virasoro algebra. Okay, so let's, this is an important, and so we're going to do all the steps, and luckily it's not very difficult. So let's go ahead and compute the Virasoro algebra. So we need to do the residues. So let's look at that. So I have a residue Jm Jr. So this is the same as a residue Z1 n plus 1, Z2 to the n plus 1. And then I have T of Z1, T of Z2. And so in order to compute this residue, I have to know what the singularity structure there is, right? So this equals to residue Z1 n plus 1. So and remember, we're not looking at the residue at 0, but we're looking at the residue when Z1 approaches to Z2. So in particular, this guy, does this guy have a residue for say negative M or N, or for any M? Does it have a residue? A residue, Z1 goes to Z2, Z1, n plus 1, Z2, n plus 1 equals.
There's no residue.
No residue, right. There is no residue because this function is not singular when z1 equals to z2. This is simply z2 to the power something. And our z2 is not at the origin, right? So that's why the residue is 0. Okay? So the residue can come up. Now you know that the residue can come up only from singular parts in TT. So it can only come from the singular part of the OP. That's why I'm justified to just care about singular part. And so the singular part is C over 2, Z12 to the fourth, and then I have plus 2 over Z12 squared P. Right? And so by the way, so here, this guy, I have to think as being evaluated at Z2. And then I have plus 1 over Z12 del Z2, and that's it. So there are non-singular parts anymore, and the non-singular parts will not produce any contribution to residue because this doesn't have any residue. Okay, so very good. So let's see what will happen. So how do where the residues will come from? Well, definitely the first term will produce a residue. So here we have a fourth pole, and the residue is the first pole. So in order for me to get the first pole, so this is just a constant. So this is C over 2. Z2 is also a constant. So I have Z2 to the n plus 1. How do I produce? I have to expand this function around Z2 to the third order, right? So let me do it one time because, okay, I'm going to do it here. Is that all right? So what I'm going to do, I'm just going to say that Z1 is Z2 plus Z1 plus del Z1 over, it's not. So if I have a function f of Z1, right? So I can write this down as f of Z2 plus f prime Z12 over 1 factorial plus f double prime over 2 factorial Z12 squared, and so on. Just a Taylor series expansion. And these derivatives must be evaluated at Z2. Right. So here I have that to the fourth, and my function is Z1 to the power m plus 1, so I need to take a 3 derivative. So that's 1 over 3 factorial del 3 of Z2 m plus 1. Okay, so that's a contribution to the residue. Then the second piece plus 2. So notice that what's happening is that, well, this is just a constant, so n plus 1. So this is a second order pole, so in order for me to get a residue, I have to differentiate this guy once. So I have 1 over 1 factorial del Z2 over n plus 1. And then I have left with this t of Z2. And then there is the last piece, and the last piece has a simple pole. So in order for me to get a residue, I cannot take any derivative here. So I'll just take Z1 equals to Z2. So I have plus Z2 to the n plus n plus 1 del of t of Z2. Okay? Yes?
Should it be m plus 2?
Sorry, yes, it does. Okay. Good. Very good. So we're almost there, right? So we computed the residue, and now we want to write it down in a nice form because our goal would be to compute the integral, right? So around that. Okay, so this equals, So the first one, you can believe me, I can compute this derivative. So this is C over 12, m cubed minus m. And then I have z2 to the power m plus n minus 1. Okay? So, so the second piece gives me plus 2 m plus 2, and then I have z of m plus n plus 1 t, and then I have plus z, okay, z2. Can I drop z2, guys? Okay, z2 is going to be our new z. Okay. So plus z, and so here is m plus 2 del t. Okay, so any questions so far? No? Okay, so now I'm just going to write it down C over 12, m cubed minus n, z to the m plus n minus 1. So here I'm going to write it down as m minus n, z to the m plus n plus 1 t. Okay? And then I have plus additional piece. So notice that what I did, I actually took some part from here. So the part that is left is m plus n plus 2. Okay? So if you add those two guys together, you get 2m plus 2. Then m plus n plus 1 t plus zm plus n plus 2 del t. Okay, so just stare for a little bit to see that I didn't cheat. And all I did, I just regrouped terms in certain way. So this regrouping will help us compute the Z2 integral. Okay, so very good. So what do we have here? Notice that this combination up here is a total derivative. So it's del of z m plus n plus 2t. Okay, so we have three terms. One term, there are two terms there, and then there is a total derivative. So the last step after we do the residues, right? After we do the residues, we have to compute the integral with respect to z variable, right? So our Virasoro algebra, the commutator algebra for the Virasoro generators takes this following form. So I have Lm comma Ln commutator integral dz over 2 pi I. And so there are these three pieces that we computed there. So that's C over 12, and then m cubed minus m. And I'm going to write it down divided by that. So that's the first piece. So the second piece plus m minus n, and then z m plus n minus 1. So it's plus 1, right? It's the plus 1. Times t. And then there is one more piece, which is the total derivative, m plus n plus 2 times t. Okay, so now, what is the integral of a total derivative? Vanishes, right? So beautifully, we don't have to worry about that. So the first guy, we can use the residue theorem again. So I have 1 over z, so it's the only time it will contribute when n and m, n plus m equals to 0. So this guy equals to c over 12, m cubed minus m. And then I have a chronicle symbol. m comma minus n. So the only contribution there comes when n plus m equals to 0. And the last term, I have plus m minus n. So actually, that integral is our favorite Virasoro generator, m plus n, right? So remember that Virasoro generator L sub k is dz over 2 pi I z, z to the k plus 2 of the stress energy, which is exactly what we have here. All right, very good. So this is our Virasoro algebra. So now those are operators that act, those are conserved charges, right? They act on Hilbert space and they satisfy the following condition. Let me write it down. I want to write down the same order. Kolchinsky does it and everything else. And of course, there is a corresponding algebra for the anti-holomorphic set. Yes.
M and N, they can be both positive or negative?
Yes, because those are the guys in the Laurent expansion. Just because the function is holomorphic, it doesn't mean that it can be expanded only in Taylor series. Right? Okay. So it's an integral, I mean, but it is true that locally any holomorphic function can be represented as Laurent expansion.
So with this first term, wouldn't you get other contributions other than just when
This one?
n
No.
is equal to minus n?
No.
Wouldn't you,
No.
like say,
They are
being 1
integers,
over?
right? M and N are integers. That's what we worry about, right? But even if they wouldn't be, right? So, or if you wish, you ask what the residue here is. So you can compute this integral by using residues. That's still an integral around 0. So the residue is 1 over z. Doesn't work. So I still can convince you. The way to do this is an integral, right? So so this integral is an integral with respect to a holomorphic variable. So it doesn't matter where I put my point, right? So what I could do, I can think of this as an ordinary integral. So I'm going to say that my z, so my contour c, I define my contour c to be absolute value of z equals to 1. So I integrate around the unit circle. And so what I can do, I can say that z equals to e to the I alpha. And so now this contour integral becomes an integral from 0 to 2 pi. So here I have dz. So it's going to be equal to z, right? Well, so it's going to be equal to e to the I alpha times I d alpha divided 2 pi I. And then I have, keep that here, I can divide by z. And then here I have e to the I alpha m plus. Right? So that will cancel, and so this integral will become just an integral, ordinary integral with respect to alpha. If you compute this integral, it will be a sine and cosine. And you will find out that it actually vanishes everywhere unless m plus n equals to 0. But what I did, okay, it's, the simplest thing to think of this is that look at this function, right? So this is a holomorphic function. And the only contribution of the function is the residue of that function. So the residue of the function is whatever is left after you took out 1 over z. I take out 1 over z, I have that to the m plus n. So unless m plus n equals to 0, in this case I have 1. In any other case, I just don't have it, right? I will have either the divergent piece, but the divergent piece will cancel if you integrate over the full circle. All right, guys, so any questions about the Virasoro algebra? No. So now once we have, oh, sorry, yes. and m are integers. Remember that the way how what are these Virasoro generators, right? So those are charges associated with the current, and the way how we constructed the current, we took a stress energy tensor, we multiplied Jm by Zn plus 1. Is there any constraint in which this Jm is no longer a conserved current? And the answer is not, because Jm is conserved every time it is holomorphic. Positive and negative. Yep. Very good. Move ahead. So now those guys are our operators on the Hilbert space, and so I can define my Hilbert space to be, as a space of states which are eigenstates with respect to some of those L's. And so in particular, we'll talk about that later, but now let's study some properties of this Virasoro algebra. Properties of Virasoro algebra. So I can put n equals to 0. So if I put n equals to 0, so I have a commutator of L naught and n, and so this equals to minus n L sub m. And so this immediately tells me that if I define my Hilbert space in such a way that I have a state which is an eigenstate of L naught, so L naught psi equals to H psi, right? So then if that is the case, then this guy M psi will be an eigenstate of L naught as well. Is an eigenstate L naught as well. So in some sense, what I'm doing, I'm constructing a Hilbert space, much like you would construct a Hilbert space for a harmonic oscillator. Right, so I choose so this is like a ground state you can think of, except that it carries some non-trivial charge H. Not as surprising, this is what will end up being the highest, will end up being the holomorphic rate of the field. And so here I claim that this is still an eigenstate of L naught, and in order for me to see this, I have to act with L naught on the state, and I can use that commutation relation here. So this guy is L naught Ln equals to minus n Ln plus Ln L naught. So this is the same. This is the same as Ln L naught psi, and then we have minus n Ln psi. Right? So by assumption, psi is an eigenstate of L naught. So I have H Ln psi, and then I have minus n Ln psi. And so we are finding that indeed the state Ln psi is going to be an eigenstate, and an eigenvalue is going to be H minus n. So with this trivial analysis, we concluded that acting with Ln of positive n will decrease the weight, and acting with negative will increase. So kind of analogous to creation and manipulation operators. So generators. So our conclusion: generators. With positive n lower h, and with negative raised h. So So notice that that operator has an anomaly, right? So there is a central charge entering in Virasoro algebra, right? So there is an anomalous term. But there is a special subalgebra that the Virasoro algebra has, which does not depend on the central charge. So there exists a universal, meaning that it doesn't matter what CFT you have, a universal subalgebra of a Virasoro algebra. Meaning by subalgebra, meaning that it closes, so I have to specify new generators and say that they actually have commutations only in between themselves. And those guys are L naught and L plus and minus. So by plus and minus, I mean plus minus 1. And so those guys have an algebra of the following type, closes between themselves. That's why it's a subalgebra. So L naught, L minus 1 equals to L minus 1, and then L1, L minus 1 equals to L naught. Okay? So, so if you ask, so there is some subalgebra, is there some classical algebra associated with these commutation relations? And the answer is yes. So this is SL2R. So this is the algebra. This is a subalgebra of conformal transformations, which are just rigid scale transformations and rotation. Right? Good. So any questions? Very good. So what we did, so we started. So let's now take kind of a bigger perspective. So what we did, we had a stress energy tensor, which was a operator in our CFT, which had a Z dependence, and then given that operator, what we did, we went into the idea of finding a representation of the CFT operator on the Hilbert space, and we did that through the Laurent coefficient. Laurent coefficients of T of Z. And so remember the way how we define these Laurent coefficients, we simply said that T of Z we need to represent, if it's a holomorphic operator, we're going to represent it as a Laurent series from minus infinity to plus infinity. And so here we had L sub m over Z m plus 2. And then we use the whole structure of the OPEs in the conformal field theory in order to understand how this Virasoro Laurent coefficients, which are Virasoro generators L sub m, act on Hilbert space, what kind of algebra they have. But the point is that we can do that for an arbitrary operator, right? So let's suppose we have an operator O, which is a holomorphic operator, and so here it was natural to introduce a factor of 2. Remember the reason why that factor of 2 showed up, because that 2 was canceling after we went into an omega frame. And so in general, it's natural to think that if you have a holomorphic operator, you can do a Laurent expansion for it. So it's going to be an expansion from minus infinity to plus infinity again. So then you have coefficients O sub m, which will end up being operators acting on the Hilbert space. And in the expansion here, we have, instead of m plus 2, we will have m plus h, where h is a homomorphic way of O. Okay, so we're assuming that that O is our primary field. So assume that O is a primary operator, which simply means that T of Z O equals to H over Z square O plus 1 over Z del O. Okay, so we know the OPE of this operator was a stress energy tensor. And so now we can go ahead and compute a commutation relation, right, between Laurent coefficients of our operator and the Virasoro generators, right? So in other words, we can ask the question, what is this commutation relation equal to? And so that's going to be equal to an integral of dz2 over 2 pi I, right? And here we have a residue as z1 goes to z2. So there will be a conserved current associated with this charge, which is Jm of Z1, and then my operator is at Z2. So this is something that we discussed earlier today. And so this conserved current is simply Z Zm plus 1 times the stress energy tensor. And so once we know that our operator O is primary, we know the OPE, so we can go ahead and do this exercise, which I'm not going to do. It's a straightforward exercise, and if you understood everything we discussed today, it's easy to reproduce. So you will find out that it's h minus 1, m minus n, and then I have O. Okay, so now you can roughly see the idea. So we have a Hilbert space of the CFT. We can construct that Hilbert space by thinking of it as being constructed from eigenstates of L naught, and then we understand how various operators can also through these commutation relations. We understand how various primary operators act on this Hilbert space. Okay. So good. Now, what I'm not talking about, and you have to do it for yourself. So everything that I talked was in the context of closed strings, and in fact, I just looked at the holomorphic sector, and the holomorphic is identical. But you can go ahead and do the same thing for the open strings, and you can read in how to do that. So in the remaining 7 minutes, until we are kicked out, I'm just going to start down and now what we want to do. So notice that everything that we did was very general. I was talking about a general CFT, which has an arbitrary central charge. All I care is that that CFT, if you think, has the, it's formulated on a plane, right? So there is this that plane. So we constructed a Virasoro algebra, and pretty much everything was very general. So now what I want to do, we want to go back into the free CFT of a single scalar field, and we're going to study how does this Virasoro generators, how are they represented in terms of the coefficients of the mode extension of our field, right? And that will be, we discussed this, so what is left in the CFT for us to do? So after we do that, then we will go and study vertex operators. We study correlation functions in the CFT. And after that, we're done. You all are experts in the CFT. So, so the last thing I want to show, actually, definitely we will not finish today, but at least we can start. It's mode expansion. So what we, again, the logic here is that we want to look at a specific CFT, and there is a specific field in mind. So we look at the CFT of a single, well, not single, of the scalar field, so there is an index mu. So in general, X mu has homomorphic and a homomorphic part. And so it doesn't have a well-defined, Laurent expansion like we discussed before. But what does have a nice well-defined Laurent expansion are the holomorphic and anti-holomorphic derivatives of this field, right? So remember that del of X mu is holomorphic, and del bar of X mu is actually anti-holomorphic. And so what this tells us, that according to the general discussion, it must have mode expansion, right? What they did there was a mode expansion, and 3 minutes. So we're being kicked out. I'm just gonna write down mode expansion, and we'll go. I know he seems bully. He cannot bully us, right? We'll do a little bit more than that. So let's do mode expansion, right? So I'm doing exactly up here, right? So I have usually that I define some arbitrary coefficients which are useful to. So it will be useful to relate to our previous discussion. So I have minus I alpha prime over 2, 1/2, and now I have my mode coefficients. Alpha subscript m mu, so those are analogs of O sub m, and then I have to divide that m plus 1. The reason I have to divide by 1 is because the conformal weight of del x is plus 1. So here is the summation from minus infinity to plus infinity, and then I have del bar of x mu. So it has an anti-holomorphic expansion on the side, alpha prime over 2, 1/2, sum of alpha and mu tilde z bar n plus 1 again, because del bar has anti-holomorphic weight plus 1. So one last thing, and that's where we will end. So we want to ask the question. So here, those are the derivative of the field has a nice Laurent series, but the field itself does not. And so what we ask, is there any constraint? What kind of constraints do we have? So definitely we want this field X. Well, at least in the simplest cases, we want X to be a single valid field on a world sheet, right? So we require. So we want X of that bar to be single valued on our complex plane C, right? And so let's see what kind of constraints does that bring. So notice that what I have to do, I have to integrate both expansions. So what I have is that everything will be single valid except, so we have to look at m equals to 0 term when we do the integration. The reason is because once I integrate 1 over z, I will get log z. And so the first guy will give me alpha 0 mu log z, and the second guy will give me alpha 0 tilde mu log of that bar. And so in general, this is not single valued on a complex plane. And in order for it to be a single value, I should be able to write it down in this form. So that's a bar is a single valued function. And so, so from here, you can see that that puts a constraint on the mode expansions, right, of field del operators del x and del y, and in particular, the zero modes in the expansion must be identical. All right, guys, so we'll pick up from here next week, and I should be able to come up next week with some exercises for you to practice contractions and something to play around with.